Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Irina Lebedeva. Irina is a bachelor degree student at MIT. Currently, she is an intern researcher at the Wireless Networks Lab of IATP. In her research activity, she mainly focuses on the development of 5G networks. Today, she will share with us her recent results about multicast transmission in 5G systems. Irina, the floor is yours.
Hello everyone. Let me introduce myself. My name is Lebedeva Irina, and today I'm going to tell you about efficient multicast service in 5G systems. 5G systems support different applications which have different requirements of quality of service. Our research is complicated by URLLC users' participation in transmission. URLLC users impose strict limits on transmission delay and reliability. For example, delay should be less than 10 milliseconds and packet loss ratio, PLR, has to be less than 10 to the power of -5. Some of URLC applications, such as industry optimization and self-driving, can benefit from the use of multicast transmission. Multicast is simultaneous transmission of the same data to a group of users. The straightforward approach to enable multicast is to make unicast transmission to each user equipment, UE, but this approach significantly increases the channel resource consumption with the number of UEs. Which makes up for a reason to support multicast on file level, make multicast transmission in a common time frequency resource using the same modulation encoding scheme, MCS, and precoder for all users. In 2022 year, release 17 of FreeGPP offered a set of mechanisms to support multicast in 5G systems. One of the mechanisms is multicast hybrid autonomic repeat request, HRQ, which improves reliability by retrying failed transmission attempts. So there are different feedback schemes that are used to provide acknowledge of transmission. We consider three feedback schemes. First scheme, which we call no feedback, the GNB does not allocate uplink resource for feedback at all. Thus, HRQ transmissions are not used with this scheme, and base station makes only one transmission attempt. In contrast with the second scheme called ACNAC feedback, in the GNB allocates a separate uplink feedback resource for each UE, such that the UE can send a positive acknowledgement ACK or negative acknowledgement ACK for each transmission. The third scheme, called NAC-only feedback, can be considered as the intermediate solution between previous two. The base station configures a single uplink resource in which only the UEs would have failed to decode the transmission sent NAC. Therefore, with this scheme, the GNB shadows and HRQ transmissions, but doesn't know which particle UEs required it. We consider a GNB that provides a multicast URLC service for NUEs. The latency for each packet shall not exceed decause delay, and the packet loss ratio should be less than PLR cost. A multicast packet is considered lost if it is not delivered in time to at least one UE. Since massive multiple input, multiple output MIMO is a key feature of 5G systems, we consider the GNB equipped with a large number of antennas M. Also, to provide efficient MIMO operations, the GNB uses time division duplex scheme with a periodic structure of downlink and uplink time slots. each having duration of T subslot. Specifically, the uplink resources uses for feedback from users and for sounding reference signal SRS. SRS is transmitted with the period T sub SRS, and the GNB uses the SRS to estimate both downlink and uplink channel quality. We should to configure many parameters for multicast transmission, but specification of 3GPP don't describe how to configure multicast transmission parameters to provide URLLC with low overall resource consumption. So in this research, we studied the impact of the different parameters to resource consumption. So let me start with describing how to better select the number of transmission attempts and feedback scheme. The maximum number of transmission attempts depends on the latency limitation and the time division duplex configuration. In particular, for very strict latency requirements for retransmissions cannot be delivered in time. Thus, only a single robust transmission is possible, and for moderate latency requirements can obtain the UE feedback and make a conditional retransmission in the initial if the initial transmission fails. For 2 transmission attempts, we can select feedback schemes, ACK-NAC or NAC only. And in the case of 1 transmission attempts, we use feedback scheme for MCS correction, and it is no important which UEs don't receive the data, so we consider no feedback or NAC only feedback scheme. Now let me tell you about precoder construction. The precoder selection problem is formulated as follows. For each UEI and RBGF, the base station has estimation of the channel matrix H sub IF of size 1 times M that is updated based on the periodic SRSs. Next, GNB constructs the precoder matrix of W sub F for each RBGF. And next, the base station, based on the noise power estimation and matrices of channel and precoder, calculates single plus interference noise ratio SNR for each user I and each RBGF. The problem of multicast precoder construction is formulated as one of 2 equivalent optimization problems. First one is maximization of minimal users SNRs, which constrained on precoder power, and second one is minimization of the precoder power with constraint on SRS. The problem of precoder construction is in fact hard, so there are a lot of approaches to solve this problem, and the authors of the paper 2 suggested 4 algorithms of precoder construction, which solves these optimization problems. The first, second, and third algorithms solve the second problem, and the fourth algorithm solves first problem. Next, I will tell you about RBG selection. We can evaluate the spectral efficiency for each RBG. To do this, in each RBG, we determine the minimum MCS among all users, which satisfies target BRP sub 1 for the weakest users and calculate the size of the transport block. Then, based on the calculated spectral efficiency, we sort RBGs. And now we need to select the best set of RBGs that are enough to transmit all available multicast data. We start from a single best RBG, calculate MCS and transport block size, and check if we allocate enough resource to transmit data. If resources are not enough, we add next best RBG out of the rest until the selected K-stick best RBGs have enough transport block size to transmit data in buffer. Described algorithms uses the latest available measurements and doesn't take into account channel aging that may result in data loss during transmission due to changes in channel quality. To solve this problem, we should consider channel fluctuation. So MCS is selected like sum of function by SNR and target blur and subtraction delta. There are several algorithms to select delta. First one is constant value. We use this feedback scheme, no feedback. And second one is with using outer loop link adaptation OLA algorithm. The paper 3 describes algorithm that uses preliminary rather feedback statistics to find constant subtraction that will be used without making any correction based on instant feedback. The multicast OLA. With the multicast OLA, the base station keeps a single subtraction delta sub OLA for a multicast group. OLA algorithm is updated for a unicast case, so we adapt it for a multicast case. Note that delta sub OLA is a real number, so we run the obtained after subtraction MCS to an integer value and check it with respect to the lower and the upper bound of the available MCS. The base station updates delta sub OLA based on the obtained HRQ feedbacks. Specifically, delta sub OLA is increased by a constant delta sub plus if the transmission fails. Otherwise, it is reduced by a constant delta sub minus. Note that multicast attempt fails if at least one viewer does not receive the data. The average blur provides by the multicast OLA algorithm converges by this formula in slide. In case of one transmission attempt, we can set P sub 1 equals PLR cost and select all the parameters accordingly. But in case of two transmission attempts, the base station has to select two MCS. And the simplest approach is to use the same MCS for the first and the second transmissions. The MCS sub 1 is selected using the OLA algorithm with the target blur P sub 1 equals squared root of PLR cos. And by taking into account HRQ combining gain, is assumed that P sub 2 less than P sub 1, and thus the overall reliability requirements is satisfied. Since 3 GPP specification allow using different MCSs for different transmission attempts, we propose the following approach. We select two target blurs such that multiplication of P sub 1 and P sub 2 are less than PLR cos. And for each transmission attempt, the target blur is provided by a separate OLA adjustment. To evaluate the performance of the approaches presented in our research, we use the network simulator NS3. We consider a free GPP urban macro scenario, and base station delivers a multicast stream to NUEs, randomly dropped in the base station's coverage area. The table lists the main simulation parameters. The most important metrics for performance evaluation is average PLR and average downlink and overall resource consumption. The downlink resource consumption is determined as the average number of RBs used in a slot for downlink transmission divided by the total number of RBs. The uplink resource consumption consists of two parts. First, the uplink resource is used for UE's feedback transmission, and second, uplink resource is used for SRS. For the feedback scheme, the resource consumption can be expressed like this. The B sub f is the number of RBs allocated for transmission of a single UE feedback. By default, B sub f equals 4. And note that for a NAC-only schemes, the resource consumption is n times lower than for a NAC scheme because a single feedback resource is allocated for all UEs. Uplink resources allocated for SRS can be calculated by this formula. The T sub of DM is the duration of one of DM symbol, and n sub 0 equals 4 is the maximal number of SRS that can be multiplexed in a single of DM symbol. Now let me show and describe the numerical results. In the first set of plots, considered UE moving with 3 kilometers per hour speed and SRS period 20 milliseconds. I will consider plots which show the downlink and the overall resource consumption for various configuration of transmission parameters. Note that for all the considered solutions, the reliability requirement is satisfied. Looking to the plot, we can notice that in the case of two transmission attempts, less resources are consumed than in the case of one transmission attempt. This effect differs from observed for low tolerant traffic. The multicast HRQs only negligible reduce resources consumption compared with a single transmission. Now let's compare cases with two transmission attempts and different target player for each transmission. From different configuration of two target players values, the configuration with target player for first transmission attempt equals 0.1 provides the lowest resource consumption. The effect is explained. This effect is explained by this formula in slide. The eta of P sub 1 is the consumption of a single transmission with target player P sub 1. Eta of P is a monotonous function. Since the first summand is the increasing function with P sub 1, while another one decreases, and there is an optimal P sub 1 that minimizate eta sub 2tx. Now let's compare different feedback schemes. The left plot shows that the downlink resource consumption for the ACNAC scheme is lower than for the NAC-only scheme because the knowledge of the set of failed UEs as the first transmission allows increasing SNR and selecting higher MCS for the second transmission. However, taking into account the influence of the uplink resource consumption in the right plot, the NAC-only scheme becomes the better solution. Thus, out of the three considered feedback schemes, the NAC-only scheme provides a good balance between downlink and uplink resource consumption. In the second set of plots for URLLC, we show the influence of the UE's mobility and period of SRS on the performance. Consider the case with NAC-only feedback scheme. This this target blur for the first transmission equals 0.1. Note that lower SRS period significantly up to 40% reduces downlink resource consumption for 3 kilometers per hour UE mobility. However, for 60 kilometers per hour UE mobility, the reduction does not exceed 10%. The reason is that for 60 kilometers per hour, the channel changes so fast that at the lowest possible SRS period cannot provide accurate SNR estimation. If we consider the overall resource consumption, we can see that the significant gain in downlink resource consumption is diminished because of the high overhead of SRS. SRS period equals 10 milliseconds provides a good balance between downlink and uplink resource consumption and gives up to 20% reduction of the overall resource consumption with respect to period of SRS 20 milliseconds. And now let's compare downlink resource consumption for different precoders algorithms. Note the best algorithms are SBFS and UE plus RCC2. These algorithms provide almost same downlink resource consumption. Note that according to a regional paper, SBFS has 6 times less computational complexity than iterative update algorithm. The RCC2 algorithm consumes up to 40% downlink resource more than SBFS algorithm. We studied the new multicast mechanism introduced in release 17 for URLLC traffic. And based on simulation results, we defined the most suitable parameters for reliable multicast transmission with low channel resource consumption. So we show that HRQ transmissions usage reduces resources consumption up to 60%. In case of two transmissions, usage of different players for each attempt decreases resource consumption up to 30%. NAC-only feedback schemes allows to reduce up to 25% the overall resource consumption. Optimization of the sounding period can notably reduce overall resource consumption for the low mobility scenario up to 20%. And SBFC precoder algorithm allows to reduce up to 40% the downlink resource consumption. It's all I want to tell you. Thank you for your attention. If you have any questions, I'm happy to answer them now.
Thank you, Irina, for your interesting talk. Maybe the first question from my side, and the question is, why do we need? I don't quite get the difference between ACNAC scheme and NAC-only scheme, because I don't understand why do we need scheme on slide 5 with AC and NAC if no AC. NAC only is better, has lower overhead. Could you explain, please?
Yes, of course. Thank you for your question. We use when we use ACNAC feedback scheme, the base station knows which UE receive data and which UE didn't receive the data, and we have to and the base station have to allocate the a lot of resources for each scheme, but in scheme NAC only feedback. When we use NAC only feedback scheme, the base station doesn't know which UE didn't receive the data. And thanks for ACNAC scheme, we can construct precoder more exactly, but we have to relocate a lot of resources.
So in the NOAC scheme, it has lower overhead, but the disadvantages of the scheme. So basically, my question is, why we can just always use NOAC, NAC only feedback scheme instead of ACNAC scheme?
Because based on numerical results, we can see that NAC only feedback schemes consumed less uplink resources, and so
so why do you have a comparison with ACNAC scheme? Because it seems obvious that NAC only consumes less resources.
Yes, but we didn't know it before our research, and we tried 2 schemes and received these results that NAC only scheme work better in the case of overall resource consumption.
Okay, thank you. Any other questions? The question from Andrei Belagaev.
Yes, can you hear me?
Yes, I hear.
Yes, first of all, thank you for the presentation. Yes, I have a question maybe a bit related to what Vyacheslav asked. So could you please clarify how exactly GNB reacts on ACK or NAC? So is it true that when, for example, GNB understands that user 1 has successfully received data and user 2 did not receive data because it sends NAC, then for the second attempt, it will construct precoder for only one user instead of both of them?
Yes. The ACNAC scheme. Thanks for ACNAC scheme, base station can construct precoder more exactly and relocate more power for failed users.
So, for example, I mean, we have 2 schemes for 2 transmission attempts, ACNAC scheme and NAC only scheme. And for example, let's say we have 3 users and only one user replied with NAC while 2 others didn't reply anything. Can we assume that the other 2 users just received everything successfully and construct the second attempt only based on the one user that sent for us NAC?
Yes, we make the second transmission only for users which didn't receive the data.
So for those who explicitly returned NAC for us. So we transmit the second transmission attempt using precoding for only those users that explicitly sent NAC for us, for the GNB.
Yes.
then what's the difference between NAC only scheme and ACK-NAC scheme? Could you please clarify? Because I mean, when we haven't received NAC, we can assume that we received ACK. No?
When we use ACK-NAC scheme, we know which users don't receive the data, and we can make the retransmission for these users. And we couldn't relocate resources for users which receive the data.
Yeah, and with NAC only scheme?
When we use NAC only scheme, it's enough for base station to receive only one NAC, and base station understands that it's have to make second transmission attempt, and for all users.
Yeah, that's the difference. For NAC only scheme, it transmits for all users, not for those that transmitted NAC to this station.
Yes.
Okay, yes, thank you for the clarification. And then maybe the last question from my side. You mentioned in all your figures, by the way, you do not show the slides, but yeah, if you show all your figures, they all contain only scheme with multicast. But you mentioned in the very beginning that the other very simple approach is just do unicast to all users with the same data. And then you mentioned that it's like a very bad approach in terms of peak overhead. So can you provide any idea if we compare any of your results provided in this presentation with the unicast scheme, what will be the difference between the consumption of the resources?
I suppose that the case in the case of unicast streams, we will consume a lot of resource consumption, more than in the multicast case.
But do you have any results that support that? Because if you have 25 users and you construct precoding according to your optimization problem, when you maximize the minimal SNR, that means that basically you almost always will use MCS close to 0. And then with unicast scheme, you can use the maximal MCS and maybe it will provide you better.
It's interesting. We didn't check it, but it's a good idea. Thank you.
Okay, thank you for the explanation.
So we have one more question in the chat from Anton, and the question is: could you provide some details of the experimental results from the on the slides 24 and 25? In particular, particular MCS index used. Could you show, please, these slides?
And could you repeat the question, please?
The question is, could you provide some details of the experimental parameters from the experiments in slides 24 and 25? For example, particular MCSs which are used. I guess the comparison results for both one transmission versus two transmissions and T-Blair 1 and T-Blair 2 are highly dependent on the scenario, which consists of power cell size, path loss, mobility, packet size, MCS table use, and other parameters. Have you checked the other scenarios to prove the generality and or feasibility of the conclusions drawn?
Okay, maybe let's split it into the particular parts. Let's start with the first paragraph, okay?
Okay. You want to know more about parameters for this experiment?
Let me explain my idea. I guess that this gain about 16% is highly dependent from a scenario region, and because of this, I wanna know, for example, MCS index in one ATX scheme used. For example, if you work in low SNR region, you probably win more in RBGN consumption metric. And because of it, again, in a comparison of 1TX and 2TX scheme should be more. Or and vice versa, if you work in the region of high SNRs, this gain can disappear. And because of it, I want to know in which region you obtain your results.
Okay, as I understand, the one transmission attempt consumed more resources because of we need to satisfy PLR 10 to the power of -5 in the one transmission. So algorithm uses the low MCS, and due to the base station consume a lot of resources, but in the case of two transmission attempts,
okay, I'm sorry, let me stop you. Which in particular MCS is used? For example, MCS 0 or MCS 3?
We yes, we configure the MCS thanks for the OLA algorithm. So OLA configure the MCS, and I cannot tell you about particular MCS for this experiment.
Maybe you should consider my question for the future work.
Okay, thank you.
Thank you, Anton, for your question. We also have a question from Alexei and from Maxim in the chat window. Let's start from there, Alexei.
Okay, Irina, thank you for your presentation. In your work, you consider only time division duplex scenario, but if we consider a frequency division duplex scenario with separate uplink and downlink and with much more uplink resources, which scheme will be most suitable in this scenario? Or maybe your conclusion will not change?
I'm not sure that I can give an answer exactly.
No, I understand you not provide some experiments, but as I understand, you have some trade-off between consumption of downlink resources and uplink resources. And in time division duplex scenario, uplink resources are very limited. But if we consider a scenario with not so limited uplink resources, maybe the most suitable feedback scheme change or not?
I think that the different feedback schemes also impact the resource consumption, but it's hard to evaluate the gain of this approach to our approach.
Okay, thank you.
Thank you for your question.
Okay, thank you. And the next question from Maxim. Why does resource consumption for one transmission schemes plateau at 25 to 30% level and does not increase further with higher number of users? I guess Maxim mentioned this first slide because we see plateau for one transmission.
Could you repeat, please, why one transmission attempt consumed more resources?
No, why do we see a plateau for the increased number of UEs? We increase number of UEs, but the resource consumption does not change.
I don't remember, but I think that it means that we use the similar MCS, and maybe it's the highest MCS. I don't remember, sorry. So I think that it's about MCS value.
Sorry, could you repeat, please?
I suppose that there is a plateau for the big number of users because of the similar value of MCS for these cases. And in the one time, the base station require, for example, high MCS and do not and doesn't decrease it. So it's consume a similar resources, the number of resources.
Okay, thank you.
Thank you for your question.
We have one more question from Andrei.
Yes, I just noticed when you started describing the plateau that it's also a bit non-monotonous. So when you increase the number of users from 15 to, I guess, 17, the red curve goes down. But it seems that when it should be naturally logical, if you increase number of users, then the number of constraints on your optimization problem also increases, and then you will have to use lower MCS, and then the consumption will increase. So can you explain the non-monotonous behavior of the curve?
Sorry, what monotonous you about?
Yeah, I'm talking about the dark red curve, which is upper all other curves on this slide. For example, between the 15 and 20, we have a point which is a little bit down.
Yeah, I see.
So maybe it's a simulation artifact or some randomness.
Maybe yes. Maybe it's a simulation.
Okay, thank you.
Thank you.
Okay, so I guess that's all for today. Let me thank Irina for the interesting talk. Also, I want to thank all the participants of the seminar for the active discussion. See you at the next seminar. Goodbye.
Thank you so much. Thank you. Bye.